Yeah, so I will talk about the compressor oracle technique, and I will actually focus on, in a sense, it's a basic form, which can be interpreted as a quantum lazy sampling technique. So let me start by, okay, let me see. Okay, a very quick, brief introduction about random oracle, which Gojan already mentioned. So I can make it even shorter. So this is the model we all know, where uh, we are in the idealized model where everyone has access to a truly random hash function. So in the quantum setting, um, additional power for all the parties is that, especially for quantum parties, is that they can have a quantum superposition to the oracle. So a quantum party can send a superposition query to the oracle and then gets the answer uh, also in superposition about the oracle. So as Gojan already mentioned, this is a model that's needed to capture the security against quantum adversary in the random oracle model. And in many cases, it could be much difficult and much more challenging to prove security in this quantum random oracle model. There has been really a lot of progress improving Qron security in the past few years, like one way to hiding lemma, compressed oracle, quantum rewinding technique, etc. You will hear a lot more later today, I think. So in this talk, I will focus on introducing this compressed oracle technique. This is a powerful tool to reason about. One of the few powerful tool to reason about Qron security with many applications, and it's proposed by Mark Gentry in 2018. Okay, so as already mentioned also in the title, I will going to talk about it in a basic form as a quantum sampling technique. And since it's more basic, I think in a sense, this could be a best way to understand the technique. And that's also typically how I think about technique. Um, so what I'll emphasize is that when you think about it in the right way, this compressor technique is able to kind of mimic classical lazy sampling technique kind of very closely. And to the extent that actually it is possible to formalize a framework to capture certain class of classical lazy sampling proof argument and can generically lift the classical proof to the quantum proof. And you can do it in a way such that using such a framework uh, uh, to prove Qron security, you can do it with a purely classical reasoning that all the quantum aspects can be hid inside the framework. But since in this talk we are talking about the technique itself, so I will follow closely the presentation to this framework, but I will unfold the underlying technique and try to tell you why such formulation is possible, kind of.
Can I come
So
in?
yeah,
Sorry.
sure. Mm-hmm.
Unfortunately, our audio setup here in the room is a little bit limited. So if you have any way to increase the
Oh,
output volume of your microphone or speak louder, that would help us over here because we are
okay.
kind of at maximum volume.
Let me
Sorry about
see.
that.
Yeah, sorry. um, so if I speak in this volume, is it okay?
Yes, it's much better.
Okay. So
Great.
I guess I'll just closer and then speak louder. Hopefully
Thank
that
you.
will work. Yeah, thanks. Okay, so I will do it by focusing on two simple example problems. I would use compressed oracle technique to show how to prove the hardness of finding pre-image of zero in a random oracle, and also the hardness of finding a collision in a random oracle. So those are very basic problems that we will focus on. Since I said that this is uh, this compressed oracle technique can mimic classical lazy sampling technique very closely. So let me start with something very simple, just to review how this classical lazy sampling idea works, and then we will gradually uh, kind of introduce ideas to move it to the content setting. So the following few slides will be extremely simple for everyone, I believe. So okay, so in the classical sampling, lazy sampling view, instead of sample this random oracle at the beginning, the whole truth table of the oracle, we will sample it on the fly. So we will initialize our oracle as an empty function that contains all the but in every entry. The but just means it's not yet sampled. And then upon every query to set a point x, we will sample this entry uniformly if this entry is not sampled yet. So it's easy to see that if the oracle is queried by an algorithm for Q queries, then this oracle D sub Q will have at most Q non-but entries. And this non-but entry kind of record what the algorithm know about the oracle. So throughout the talk, we will refer to D as the database that record the information that the algorithms know. Okay, so and it's easy to see that this view is equivalent to the original view. And the one particular way to go back to the original random oracle model is to just sample all the unsampled but entry in the final database. Then we will get an identical distribution of the oracle. Okay, now let's try to apply this lazy sampling view to a very simple example of finding zero pre-image in the random oracle. So suppose A is a Q query algorithm that try to find the pre-image of zero. So it try to find some x such that h of x equal to zero. To show that so our goal is to upper bound the success probability of A by the number of queries. So here we will show that it's upper bounded by Q over M roughly, where M is the image size of the random oracle. So the proof is basically two-liner. The first is to just observe that this DQ only contains Q random entries. So the probability that one of the entries is zero would be at the most Q over M. And then we show that if at the end of the algorithm, if the database does not contain zero, then it is unlikely for the algorithm to win. Since after the query, all the algorithm know about the database are those Q points, and those points are non-zero points. The only chance that this algorithm can win is to output some x for which it does not know the value. And this value will be random, so it will be equal to zero only with probability 1 over n. So combine the two, we can get the desired bound in the classical case. Okay, so far it's very simple. So now let's try to mimic this reasoning in the content setting. So what we need to do is to reason about a quantum algorithm that making Q queries to the random oracle. And we want to formalize basically the following four things happened in the previous argument. First, we need to have a way to say that the oracle is initialized as an empty database in some way. And then we want to argue that this database can record algorithms query the information also in some quantum way. And then we want to, as we see in the pre-image finding example, we want to upper bound the winning probability of the algorithm by upper bounding certain probability that this database has certain property, and then show that the algorithm cannot win if can only win with very small probability if the database does not have this certain property. Okay, and this will be done by several kind of clever but equivalent transformation to view the execution of this contents algorithm in the right way, including basically three steps. This following three steps that I will talk now. Okay, so before talking about the steps, let's just kind of fix the notation and then say a little bit about how we want to describe a content oracle algorithm in the random oracle model. So I will just have four registers, X and Y are query and answer register, and W model the internal working space, and the oracle register. And this algorithm A can make query, and this query is modeled by this O operator that act on the query and answer register as well as the oracle itself in the standard way, where the oracle would just XOR the value to the answer register. Okay. Now a Q-query algorithm will also can be specified by Q plus one unitaries, just model what the algorithm do between the queries. And so the final state of this execution can be described in this content state. So this is the initial state of the algorithm and the oracle. And we will do a sequence of unitary and query and unitary and query. This models a general algorithm. Okay, now starting from this, okay, sorry, I should use, okay, starting from this general view, let's go through the first step, which is very simple. So in this model, this random oracle is sampled uniformly at random at the beginning. Equivalently, we can,
Min,
uh,
sorry, can I
yeah,
interrupt you for a question?
sure, yeah,
Can you go back one slide?
yeah, here.
Okay, so the point is like, first of all, we query the oracle so we get the state somehow, right? So is the state getting measured or not after we get it? Because we cannot like make the same state for ourselves as well. So if the state at any point is getting measured, then we don't have to do it.
So the question is basically, is there any measurement involved in the oracle procedure?
In the oracle procedure,
Yeah, basically when an algorithm runs, like whenever the oracle is queried, is anything measured?
Okay. Yeah, so I will take the pure state picture. So I will assume that all the measurements are deferred to the end. So over the execution of the algorithm, there will be no measurement and just unitary operators acting on the space.
Q samples, let's Q query. Do you Q query and after that you can do a measurement or something?
Yeah, can we do a measurement in the end is now the question.
Uh, yeah, that's something I think Gojan also didn't talk about. So there's this general principle of deferral of measurement, which is a generic argument says that you can defer all the measurement if you have sufficient NC. So I guess the short answer is yes. This is without loss of generality.
Yeah, so basically, yeah, it's without loss of generality to have no measurements in between, but in the end, there can be a measurement. Yes. Thanks.
Yeah, thanks. Yeah, so I forgot to mention, yeah. So feel free to ask question at any point. It's meant to be a tutorial, so it'd be nice to clarify all the questions. Yeah, okay. So let's go through the first transformation. Okay, so yeah, so instead of sampling a random oracle and then given to a content adversary, equivalently, we can initialize the oracle state as a superposition state, this one here, and then measure this superposition oracle in computational basis. This will also give us a random classical oracle. And here, by noting that this algorithm's operator, both this U and the query operator O, are commuting with the measurement on the superposition oracle, we can defer this particular measurement, and we can think of the algorithm as running with respect to a superposition oracle state phi 0, and at the end, measure this oracle phi 0 in computational basis. This will give us an identical experiment in the random oracle model. Okay. Now, the second step is try to look at this superposition oracle view in the Fourier basis. So each entry of the oracle is a value in 0, 1 to the m. So this will be its a computational basis, the natural computational basis. Now we will take the simple Fourier transform, also Gaussian mentioned, just do Hadamard, and this will give us a Fourier basis y hat. So as for notation throughout the talk, I will use the hat to denote a state in its Fourier basis. Okay. Now, there are two crucial points when we look at the Fourier basis. First, if you have a uniform superposition state in this register, when you take the Fourier transform, you will become this zero state in Fourier basis. And second, this query operator, so think of y prime as the value in the oracle, and the query operator will XOR this y prime to the answer register y. This query operator, if we view this operator in the Fourier basis, it will kind of reverse the way it operates. So instead of XORing the answer, the value from the oracle to the answer register, you will now go back to XOR the value from the answer register to the oracle register. And this is a kind of useful fact with multiple applications, including quantum algorithm and also crypto. And it can be kind of proved by a simple calculation. Okay, now in the Fourier basis, using this observation, we can write down this query operator in this way. So now, instead of XOR information from the oracle to the answer register, now we are XORing the information from the answer register to the oracle in Fourier basis. Since we said that the oracle state in Fourier basis start with 0, and each query will XOR to only one point. So after Q query, this oracle state contains at the most Q non-zero entries in the Fourier basis. Okay, so this kind of start to feel closer to the lazy sampling view, where we start with an empty database, and then we make, after making Q queries, we will have Q non-zero entry, non-bot entries. But we need to take one step to make it formal and useful. So this is the last step of the transformation, where we will compress the oracle in some way. And this is, in some sense, the key idea in this technique. Okay, so now what we do now is to first extend this register for the oracle value, one entry of the oracle value, by one extra dimension. And we will denote this extra dimension by but, this but symbol. So originally we are in a 2 to m dimension space. Now we are in 2 to m plus 1 dimension space. And we will do so in a particular way, where we will take the direct sum of the original space with this one single dimension space spanned by but. Now, by definition, since this is a one-dimensional space, but will be itself a Fourier basis. And we can naturally extend this to the whole oracle register entry-wise, and we will denote this larger oracle space as CO. So this will be just the same as O, but each entry gets one extra dimension, but. And so CO will consist of all the databases, which are functions mapped to 0, 1 to the m or but, and contain all such functions as the basis. Okay. Okay, so now let's define a kind of the interesting operator called compression. And this compression operator will act on the X entry, and it will do a very simple thing in the Fourier basis. So what it will do will be just basically swap this zero component in the Fourier basis with the introduced but component. Well, the zero will become but and the but will become zero. And we will, okay, so this is a, simple definition, and then we will define it naturally to the whole oracle. Now something interesting to start to happen. So by definition, if we apply this compression operator to the superposition oracle state we mentioned, we will get a state that contains all but in every entry in this CO space. And this is kind of just a notation that given a state in the original oracle space, if we apply, after we apply the comp operation to it, we will call this the compressed version or compressed oracle of phi. Now, let's further see. Okay, so maybe I can pause here for questions. Is there any questions so far for the definition?
So the question is what the state phi 0 is. I guess it
Oh.
was on one of the previous slides, right?
Yeah. Okay, yeah. So it's here.
Here, yes.
Because, yeah, this phi 0 is a uniform superposition over all possible oracle. And since it's a uniform, yeah.
Right. So that it's a uniform superposition over all. It's the uniform superposition on the register, right? And now can we go back to this to the current slide?
Yeah, here.
Yeah. Okay. Are there more questions? Okay. I think you can go on time, and we can maybe take a try to recap this during the coffee break.
Sure. Okay. Yeah. Okay. So let's see a few more magic happening now. So now we have defined this compression operator that kind of take an oracle in the original space O to a oracle in the compressed space CO. Now let's try to see how to define also query operator in this case. Okay, so recall that we have this query operator to the original oracle defined this way. Now we want to define a corresponding query operator to the compressed version in a kind of operational way. So what should be the right definition? So, and what our goal here is to define it in a way that to make it equivalent to the original query operator. So the definition is easy to think about operationally. The idea now is to just to decompress it. So taking the state from CO, this compressed version, back to the original version, and then just run the original query operator, and then we compress it again. So if we apply, so the point is that if we apply CO to a state that is compressed by the comp operator, this will be equivalent to we apply just the oracle to the uncompressed state.
Kaimin, there's a question.
Yeah.
So the question is, it seemed like we compressed the Fourier oracle, but but now we have the standard oracle. So how did that happen?
So do we compress the Fourier oracle? Okay. So the idea here is that okay, this operators is a basis independent concept, and we are define it using the right basis so that it's easy to describe it. But once we define it for every basis, this will be a well-defined operator, and we can try to understand this operator in different bases. And as we will see is that some magic come from like we switching back and forth between Fourier basis and computational basis. And when we do it in the right basis, it would capture this lazy sampling aspect. So, okay, I guess for now, mathematically, I'm defining it using Fourier basis just for convenience so that I can write it very explicitly. But after I write this, this will be a well-defined operator. Is this fine?
Yes, thanks.
Great. Yeah, okay. Good. Okay, so let me move on to just try to understand the behavior of the algorithm in this compressed version. So let me just describe this execution of this algorithm. Instead of interacting with the original standard oracle, now interacting with the compressed oracle. And I will also alternatively say that we will run this algorithm in this compressed oracle view. And again, the point is that we want to make sure this is equivalent view to the original view. So the idea is simple. We just keep the state in the oracle state in this compressed version. So in the original random oracle view, we will start with the initial superposition state phi 0. Now in this compressed view, we will start with comp of phi 0. So it's the compressed version, which is all but. And now for every query to the oracle, since now we are querying this compressed oracle, so we will replace this query operator O by this compressed version CO. So basically just follow from the definition. Note that at the end of the execution, if we kind of decompress the final oracle state, we will get back to the original execution of algorithm interacting with the random oracle. Okay, so this is also one of the important point that I hope everyone understand. Okay, now let's try to understand this compressed oracle view better and see what kind of magic is going on. So the first observation is that it's about the size of the compressed oracle. Okay, so recall that when we look at things in Fourier basis, we say that after making Q query, the oracle state will have at the most Q non-zero entries in Fourier basis. And the difference between the standard and the compressed view is to just compress the oracle state. And this amounts to just a switch between 0 and the but in Fourier basis. So after making Q queries to the compressed oracle, the compressed oracle state will also only have at the most Q non-but entries. And this holds in both Fourier and the computational base. This again, by definition, since we define the extended space by a direct sum. So the Fourier transform of but will still be but. Okay. Now, so we can maybe take a step, pause here and then see what we have done so far. So we have kind of mimicked the first 2 points of this lazy sampling argument. In this compressed oracle view, our compressed oracle state will start with O but state. And after Q query, we will have a state that has at the most Q non-but entry. So in a sense, the next thing we want to say is that this Q non-but entry will somehow store the information that record the information that the algorithm that in some way. And that's what we want to understand in the next step. Okay. So now.
So sorry, Taimin,
Sure.
it would be good if we could take the break soonish. So if there's a natural point where you can take the break soon in your talk, that would be great.
Yeah, okay, so maybe let me do this. I'll just finish the 2 slides, and then there will be a point to digest and then maybe ask question when we resume.
Okay.
Yeah.
Thanks.
So yeah, thanks. So okay, so let's try to understand this compressed query operator in the right basis, and the basis we are going to choose will be kind of this one here. We will think of the answer register in Fourier basis, but somehow later on we will try to think of the database register in computational basis. And it's this funny combination give us the interesting interpretation. Okay. Okay, so here the point is just to say that since in the Fourier basis, this query operator acts by kind of XOR information to the oracle, this will also be true if we consider the corresponding CO operator when we also write the answer register in the Fourier basis. And so this CO operator can be written in this form. So when we write the answer register in the Fourier basis, this CO operator will not modify this register, but will only act on the database register. And next, we will try to work out this CO operator in the compressed basis. So maybe let me briefly mention what's going on in the next 2 slides, and then I will take a break and then I'll resume slower on these slides. So the point, kind of the punchline I want to make is that when we look at this CO operator in this funny basis, it will kind of mimic the classical probability transition matrix in the classical query. So in the classical query, roughly if the entry is spot, we will sample it uniformly, so we'll get a random value. But in the classical case, if the entry is a fixed value y, then we will stay the same. And in the quantum case, when we kind of write down this CO in this basis, we will get a similar aspect behavior to this database register in the computational basis, but with some caveat. So I will pause here and then explain the caveat when we resume. So let me try to recap. So far we have done a sequential transformation, and then kind of switch back and forth in different bases to try to look at things in the right way or in a good way. So far we have defined a compression operation that kind of compress or take the oracle state to its compressed version, and we can also take it back. And this compressed operation is defined very simply in the Fourier basis by switching between Fourier 0, and the extra but dimension we introduced. And after we define this comp operation, we can also consider query to the compressed version of the database or the oracle. And this can be defined in a natural way by saying that we first decompress the state back to the original space and then make the original query as before, and then compress the state again. And by looking at things in this way, we get the execution of a quantum oracle in this compressed oracle view. And we will further understand this execution in this compressed oracle view on the proper basis. And we will see how it mimics the classical lazy sampling argument well. And it's also a simple observation that by this definition, the compressed view and the kind of original or standard view only differ by a compression operator on the oracle register. So we can move from compressed view to the original view by just applying this comp in the inverse of comp, the decompression operator. And we have see some observation about how does the size of the compressed oracle in this compressed view behave in a way that's already kind of mimic the classical lazy sampling view in some way. And now we are going to kind of try to understand this compressed query operator more closely to see how it changed the compressed oracle in the right basis. So this is where we are. So let's do this again slowly. So the basis we will choose to understand the behavior of the oracle is this one, where we will take the answer register, look at the answer register in a Fourier basis. In this way, this query operator will write the information from the answer register to the oracle instead of the reverse direction. And we will look at this compressed oracle in the computational basis, since this is the value we care about. The algorithm and the kind of the success condition, winning condition is defined in the computational basis. So we will choose the database in the computational basis. Now, looking at this compressed query operator, this in a basis where the answer register is in Fourier basis, this compressed operator will act only on the database register. And our next step will be to write down this compressed query operator in computational basis for a particular entry X that's being queried with a certain value of answer register Y hat in the Fourier basis. So we will not do calculation here. I'll just show you the result, but it's a kind of exercise in linear algebra to write down it precisely. And we will also not show you the precise value that will depend on the phase on this particular value of Y hat. I will just show you the magnitude of this value. So by working out the value, you will get this matrix. And we will, as mentioned before break, we will try to compare this matrix with the transition matrix of a classical lazy sampling oracle when the entry is being queried. So maybe let's look at what do I mean by the classical probability transition matrix in the classical case. So in a classical case, if we have an oracle entry X that is already sampled, since it's a classical value Y, this will stay in Y. So if you look at the column of this transition matrix, it will just be 1 in the diagonal and 0 in the rest. Just means that the value will stay the same. If we look at if the entry is but, then when we query this X, we will sample this entry uniformly. This will corresponding to the first column here, where we will start changing the but value to a uniformly random value. Okay. Now, let's try to interpret this matrix we have worked out in this basis, and we will see a similar interpretation. So maybe let's start with but. Suppose this entry is not queried before, then in the compressed oracle, it will be the but value. And when we query it, we will basically multiply this matrix with this but vector, and then we will get this state here. And as we will see, it will be a kind of a quantum version of sampling, because we will change from but state to a uniform superposition over all possible value in the computational basis. Now, suppose, so this part is perfect. Now, suppose the oracle value, the original oracle value in the database is y. Then after we apply this CO operator, we will get this column here. And we'll see that it will not stay the same in y as in the classical case. It will stay the same with largest weight, or maybe informally called probability, with high probability. And it will go back to but with certain 1/square root of m amplitude, and it will be uniformly random for the remaining other value with magnitude 1/m. Okay, so kind of looking at things this way, we can just interpret a compressed oracle query as to a particular entry in this basis as trying to resample the value of the database. And as we will see in the following example, viewing it in this way, we can kind of analyze things in a similar way to the classical lazy sampling view. Okay. Okay, so let's see what we have done so far. So we have so far mimicked the first two features in the classical lazy sampling argument. We start with the compressed oracle state, which is an all but state, the empty database. And after Q queries, this database will record Q non-but entries. And in the computational basis, this essentially resamples these Q entries. I mean, the query can be interpreted as resampling the value of these database entries. Now let's try to see how we can mimic the last two steps using our example of zero pre-image finding. Okay, so now we will have to go through some calculation to understand, to kind of bound the success probability. So let's take it slowly. Okay, sorry. Okay, let's start with algorithm A, that is a Q query content algorithm. Try to find a pre-image of 0. And let's try to look at it in the compressed oracle view. And using the notation we have introduced before, the final state will be this state here. So we start with a compressed oracle state, and we do the compressed version of a query operator in between each unitary operator of the algorithm. And at the end, we will get this state psi. Okay, and what we know about it is that this database state F inside will have at most Q non-but entries. Now, to capture the output of A, we will just relabel the register into some output register, just capture that A output X, and the remaining part being some other working space. And write down this state in this basis without loss of generality, we can write it in this form. Okay.
Amen.
Yeah.
There's a question.
Sure.
When he says that there's no more than k elements that are not queries for element superposition, like the point is if you have superposition queries, you would have different queries. So is this like by element or at all? Is a general statement?
So the question is, your statement that after k queries, there's only k non-but entries in the database. How does this relate to the fact that we now have an algorithm that queries in superposition?
Yeah. So, okay. Yeah. So I should mention this point. So, indeed, in general, okay, I actually have this state here. At the end of the protocol, this will be a general state. In particular, the database or the compressed oracle state will have a superposition. And when I say that the database size by this, I mean that this would be a superposition over databases that has only Q non-but entries.
Great, thanks. I think that answered the question.
Yeah, great. Okay. Okay, so we are here. So we also use the mentioned connection. So we can easily switch back to the standard Oracle view by just decompress the Oracle. So we can also write down precisely what's the final state in the standard Oracle view, which will be just decompress the database. And since this decompression operator only acts on the database, so we can write it this way. Okay. Now we will try to compare the winning probability for this algorithm to win in the standard Oracle view versus the winning probability of this algorithm in this compressed Oracle view. And similar step actually happened in the classical case. So yeah, so I hope the definition is clear. And by the way we write down the state, we can also express the winning probability of this algorithm interacting with a standard Oracle as this expression. So it just means that we measure X and we will get output X with this probability square, I mean this probability here. And we will see if the Oracle value on X equal to 0. And we take the norm square to be the probability. And here it's in the standard Oracle view, so we will have this this decompression operator acting on this final state gamma. And in the compressed Oracle view, it will be the same probability, but without this decompression operator. Okay. And okay, so I guess I'm running short of time, so maybe I will skip the calculation. But just say that when we do this, when we try to compute the difference of these two probabilities at the end, yeah.
Just to say, you can allow yourself a little bit of time after 11:30 our time because we started late, and there's a long lunch break we can go into.
Sure. Yeah, but I guess I will still skip part of the computation to keep things more conceptual. Yeah, so so let me skip this part anyway, but just mention the high-level intuition. So when we try to compute the difference in the probability, at the end, we will need to bound the operator known of this operator. And let me just interpret what this operator means without actually tell you how to bound it. So this will capture like corresponding to the classical case where this algorithm may output some answer X that's outside what's being queried. And since this entry will be but in the lazy sampling database, it will never be a correct answer in the lazy sampling view, but it may happen to be correct in the actual Oracle. And this is this 1/n probability appear earlier in this zero preimage finding example. And this operator known also essentially captures, mathematically the difference when we switch this Fourier basis 0 with but, what's the error that can be caused by this operator. And you can bound it by a direct calculation using Frobenius norm to upper bound the operator norm, and you'll get this 1/square root of m, which corresponding to this 1/m in the classical case. Okay. And okay, so
there's a question. 1 second.
Sure.
Like it seemed that everything was just a different way of seeing the same things. I don't understand where the error was compression. Like, why is just not an equivalence way of like seeing it compressed is not the same thing as like the original Oracle by transformations.
Okay, so the question is, because the compression was just a change of basis, Alex didn't understand why the compression appears now in the analysis of the pre-image finding.
Compression is not just change basis. Change of basis will not change the state, but here is a swap operator swapping the two bases. So it does change the state. That's what I want to say. Does it make sense?
So maybe another way to put it is that the compression it transforms the uniform superposition into the bottom state, and the uniform superposition it contains all the stuff, including the zero we want to find. So we are actually taking away some of the amplitude. Maybe that can help. I don't know.
Yeah, I'm not sure I understand the key point of the question.
Here we have some kind of error that appears because of the compression. And the first view of that is that the compression is just change of the basis. Then we have this which switches our zero in the Fourier basis to this basket, and this is where the error can happen.
Yes,
as I'm understanding, because we had this basket and switched something that used to be there, but we switched it off to the budget. Am I right?
right. Yeah. So I think the confusion got somewhat cleared up. So I think maybe we can continue.
Okay, sure. Yeah, so I was going to say that if we just look at this state, there's actually a difference where we plug in this decompression operator. And so at least from the equation, you can see that there is a difference in the state.
Thanks.
And that's kind of picture here that the difference is introduced when we swap Fourier zero to but. Okay, I hope that somewhat helped. Yeah, so okay, so this is a general lemma that basically says that if the algorithm does not win in the compressed view, then the algorithm can also not win in the standard view. I mean, this true probability can only differ by a small amount. And this allows us to bound the winning probability of the algorithm by bounding the winning probability of the algorithm in the compressed view, and further by bounding the database property of the in the compressed view. And for example, in the zero image finding we have seen, this database property will just be the whether this database contains zero in the computational basis. Okay, so again, what we have done so far, we have done one more item, the last item. So we can upper bound the winning probability of the algorithm by upper bounding the probability that this database or compressed oracle state has certain property, plus some small error term.
And there's another question.
Sure.
So the lazy sampling grows the database with every query, but here you essentially still have the full database, right? At least when you uncompress, you have a database of the size of the function.
So the question is the lazy sampling, it should only basically the required state, internal state of the lazy sampling algorithm should only grow like linearly with the number of queries. But at this point, as we're viewing it right now, there's still the full state there, and it's not in the efficient form. So how do they relate somehow?
Yeah. So I'm not. Okay, so all of what I said happen in the analysis. So we don't need to care about efficiency. We don't need to care about whether this compressed view can be kind of implemented efficiently. It actually can, but that's not going to this part here. But at least we can see that that's what I emphasized before, that in this compressed Oracle view, this database will only have a small number of non-but entries, even in the computational basis. And that's how we can interpret it as recording the information that the algorithm has.
Okay, thanks.
Yeah. Okay, so let's try to at least finish this last step and then maybe see one more example. Okay, so the remaining thing we need to do is to upper bound the probability that the database contains 0 in the compressed Oracle view. Okay, essentially, and to try to motivate how we do it in the content case, let's again go back to the classical case and look at more carefully how usually the argument is done. In some sense, it's a worst case analysis, and let's try to capture this worst case analysis in the content case. Okay, so looking closely and in this particular way, we can define just ZR to be the set of database that contains 0 somewhere. And to bound the probability this database contains 0 at the end, we can bound it step by step. So if it contains 0 at the end, there must be one step that it go from not contain 0 to contain 0. And we can actually take the worst case of it, just say it would be max upper bounded by the max that the probability that the one query make any database from having no 0 to having a 0. And in the classical case, this is trivially 1 over m, and so we get an upper bound. Now, let me just try to introduce some language so that we can talk about this way of analyzing things in the content setting. So I would kind of capture this worst case analysis by something I call classical transition capacity. And this should be a simple definition, just taking the worst case. Okay, so we consider any true database property, and we want to upper bound the probability that a query make a database from having property P to having property P prime. And just a worst case notion to maximize overall possible database and queries. And we can analogically define the notion for any Q-query algorithm that turn a database in P to a database in P prime. And using this language, we can kind of rewrite the classical analysis as kind of first writing the probability want to bound a certain classical transition capacity, and then break it into one query classical transition capacity and upper bound the quantity. And this will be what we want to do in the content setting as well. Okay, so in the content setting, we will try to mimic this and define the worst case notion for this database transition probability. But as kind of maybe typical in the content case, usually we should not directly talk about probability. Instead, we should talk about the norm of the matrix or the norm of the state. So the right kind of analog of content data transition capacity should be defined this way here. And let me just try to interpret. So as mentioned, we interpret CO as a resampling operator. So we can interpret this P. So I should mention that P is a database property, and naturally I can view it as a projector that project to the database that having this property. So this P here will correspond to making sure my state has property P. And then after this resampling query, we will want to bound the kind of the magnitude or amplitude that the resulting database has this property P prime. And again, we take a max over all possible database and all possible state. And the max over the state is hidden in this definition of operator node. And analogously, we can define this Q query transition capacity. Okay. And again, the kind of to compare with the classical case, both are defined in the same worst case intuition, but in the quantum case, we work with norms instead of probability. So that's the main difference. So here's now how I want to kind of finish the proof or upper bounding the probability by this notion of quantum capacity. So again, the first few steps is what we have seen. We can move to upper bound the probability that the database contains 0 in the compressed oracle view. And this, by definition, can be written as this quantum transition capacity. And our first step that we are going to do will be to break up this transition capacity to one query transition capacity. And then the second step will be bound the one-step transition capacity. Okay. So, okay, I guess it's a bit unfortunate I'm a bit running out of time. So how much time can I have to at least finish the 2 steps?
I think 5 more minutes would be fine, if that's okay.
Yeah, okay, so I'll just let's talk about the high-level steps. So the first step is simple. We will just try to find some intermediate database property that kind of witness the transition step by step. And we can show that for any intermediate database, we can use it to break this database transition property. And to maybe just talk about our specific example, the nature property in the intermediate step will be just the property that you contain 0. And by using the lemma with all the database properties set to be 0, we can break things in this way that we have seen in the classical analysis. So since we are short on time, let me just say one word about the proof. So the proof will be simple manipulation about the operator node. We just insert this terms in the middle and then break it up using triangle inequality. And then the tricky point, one tricky point is to go from this operator node for the larger space to the space only talk about the database. For this part, I will just skip, but just mention this is based on the simple linear property about the operator node. Okay. And then the second step is to actually bound this transition capacity from database with no 0 to database with 0 by this resampling interpretation. And this first step is it's intuitive, but just to describe it needs some notation, so I'll try to skip notation. But just say that what happened here is try to say that since we only resample X, we can somehow bound this probability, the capacity by just looking at this X element and then working with just this like a 2 to n plus 1 dimensional matrix. So omitting the detail, the key calculation is here. So let me just try to interpret what's going on. So here, at the end, we want to bound this worst case norm, where we go from a database with no 0, and then we do one resampling as the way we interpret, and then it becomes 0. Since we only resample one point, it must be that this particular point becomes 0. Now, these 2 projectors, if we consider it act on this CO matrix we have worked out before, we'll see that this will kill kind of the columns and rows of this CO matrix. And the only surviving entry will be this yellow one. And we can then upper bound the operator known by the forbidden norm, which sum over the square of these yellow entries. And if you do the calculation, you'll see this is 1 over m square, square root of m. Yeah, so we have done both steps, so we basically can finish the proof this way. Okay, so maybe let me just go over the steps here, and then we'll finish the talk here. I guess that's the main point I want to cover anyway. So again, so the kind of the recipe now is that we will want to upper bound the winning probability of this quantum algorithm by upper bounding the probability that this algorithm in the compressed local view having certain database property. And then we will express this as a content transition capacity of a certain database property. Like usually, like initially, we will always start with but, and then at the end, we will have certain winning condition that's captured by this database property. And then in the analysis, we can break up this Q-query transition capacity into small ones by properly inserting intermediate database property to witness the transition. And then we can upper bound this one query transition capacity by this resampling interpretation and looking at the matrix of this CO operator. Yeah, so I guess I'll just stop here.
Let's give Kaimin a hand first. Thank you very much.